Hi, everybody. I'm Francesco Pandolfi, and I'll be talking to you about the Dark-PMT, which is a novel directional light dark matter detector based on carbon nanotubes. Now, as we know, most of the active dark matter experiments have been designed with WIMPs in mind. So this means that they are sensitive to the high mass range, but most of them quickly lose sensitivity below 1 GeV or so. However, the sub-GeV mass range is supported by many other models, for example, SIMPs. Now, to be fair, this is not the right plot you should look at because, as we know, this is the cross-section exclusion of dark matter to nucleon cross-section. And so once dark matter becomes extremely light, much lighter than the nucleus, then it'll be too light to actually create a nuclear recoil. So one of the ways to go for light dark matter is to look for electron recoils. And so for this, you can look at this plot here that was produced by Xenon 1-ton. Now, there's two things that I want to point out about this plot. The first one is that the y-axis range is dramatically different compared to the other one. In particular, limits are up to 10 to the 6 times weaker in the right plot. So this actually means that one could get away with designing an experiment with only grams of target as opposed to big ton targets. And the other thing is that most of these limits quickly lose sensitivity below 100 MeV or so. And this is because of electron reconstruction thresholds. If you have a detector which is based on looking for ionization signals in liquids or in gases, then you're gonna be having some minimal reconstruction threshold below which you're not able to see a signal. Now, our idea is to create a detector which has a solid state target, and in particular, a target made of two-dimensional materials. So, for example, graphene or nanotubes. And the idea is the following. So if you do a back of the envelope calculation, light dark matter with mass between, say, 10 and 100 MeV, part of the dark matter wind would have a kinetic energy between a few and a few tens of electron volts. Now, this is enough energy to extract an electron from the carbon lattice. The work function is 4.7 electron volts. So you end up with an electron with a kinetic energy of a few tens of electron volts. Now, such an electron would have an extremely short range in matter, but the advantage of using a two-dimensional target, a target made of a two-dimensional material, is that these electrons would be ejected directly into the vacuum. And so in particular, what we are planning to do is to design a detector with a target made of nanotubes. Now, why nanotubes? Nanotubes actually turn out to be an almost ideal target for dark matter, and the main feature they have is that they have extremely non-isotropic density, and in particular that they have practically vanishing density in the direction of the tubes. And you can see here, this is a result from 2018. This is a Raman analysis after bombarding nanotubes with argon ions. And there were two different bombardments, lateral bombardment on the sides of the tubes and longitudinal bombardment along the tubes in the open ends, let's say. And you can see here that the damaged spectrum, this is the Raman spectrum, there's damage up to a depth of only 15 microns. At 15 microns, when you bombard laterally, you already recover the pristine spectrum that you expect from carbon. This means that the damage, the penetration was stopped, the argon ions were stopped in the first, say, 10 microns. Whereas when you bombard longitudinally, the damage spectrum is found at all depths, down to a depth of 180 microns, which is the length of the whole tubes. And so this proves that the density in the direction of the tube axis is much lower than in any other, in an orthogonal direction. And so this makes for an ideal dark matter target because in a dark matter to electron recoil event, the direction of the momentum of the electron on average will be parallel to that of the incoming dark matter. And so if you put your detector with the nanotubes aligned with the dark matter wind, you're expected to see much more events because the electrons will be able to get out of the tubes, of the open ends of the tubes, as opposed to if you put the detector with the tubes perpendicular to the dark matter wind, because in that case, the recoil electron will just be absorbed in the target. So this would actually even give you directional sensitivity by design. And carbon nanotubes, vertically aligned carbon nanotubes, can efficiently be grown in the lab. There's a technique called chemical vapor deposition, CVD, what you end up with, you get these tubes which have an internal diameter of a few tens of nanometers, sorry, and a length up to hundreds of microns. And we've installed a new CVD chamber in Rome Sapienza last year. It was mainly due to attract funding. We commissioned it in July 2020 and then started growing nanotubes since. You can see here on the right that this is a SEM image of a typical growth. Here we achieved a length of 142 microns. You can see all the nanotubes in there. So what's the idea? This is the detector concept. You can see here on the left, you would have the target made of aligned nanotubes, inside which the dark matter wind would interact, kick out an electron, and the electron would find its way out of the open ends of the tubes. And then once out, the electron would feel a strong electric field with which we would accelerate it to the other side of the detector at the anode, which would be instrumented with some sort of electron sensor. Now, this detector design has actually quite a number of features. It's portable and cheap and very easy to produce. It's unaffected by thermal noise. This is because the carbon work function is sufficiently high that you can operate this even at room temperature. And then it would have directional sensitivity, as I explained to you, because of the nanotube parallelism. And the actual experiment would then be done with two arrays of Dark-PMTs. One array would be pointing to Cygnus and would be sensitive to the dark matter signal, to the dark matter wind. And then we would have also another array of Dark-PMTs that would be pointing in some other direction that would be dedicated to measuring the background in situ. And you can see here we've done a calculation to prove that this would work. You have to compare the black these are the emitted spectra, emitted fluxes of electron as a function of the recoil energy, and the black is is parallel to Cygnus, whereas red is anti-parallel to Cygnus. And you can see that there's a significant difference in the emitted fluxes of these two directions. And so this is for a dark matter mass of 5 MeV. But so this would prove that you would have a significantly higher count rate in these detectors compared to these other ones. And the other thing you have to see in this plot is that these are EV. So yeah, it would be this type of detector design would be sensitive to electron recoils down to a few electron volts. And so being sensitive to such low energy recoils means that would be practically unaffected by limitations due to minimal electron reconstruction thresholds. And so you can see that this is the expected exclusion cross section for an exposure. Well, this is 1 kilogram for 1 year, whereas here on the right you would have 1 gram for 1 year. This is the expected shape for nanotubes. Just look at the blue curve, and you can see we would be sensitive down to masses of 2 or 3 MeV, let's say. So if you put this curve, you scale it down to 1 gram, and you compare it to what was shown before in the seen on 1 ton plot, you can see that this would significantly extend the reach below at lower masses, so below 40 MeV, so already with only 1 gram of exposure. So if this is the detector concept, then there would be 2 sides of the detector, and each of them would have to be optimized. So on one side, the target, so the carbon nanotubes, we have to work on what is the optimal density, length, and configuration, and stuff like that. And then on the other side, we have to choose what sort of technology is optimal for detecting these KeV electrons that are emitted by the target. So let's look at these things separately, and let's start with nanotubes. So we are thoroughly characterizing carbon nanotubes at our facilities at Roma 3, in LASIK labs at Roma 3, where there's this beautiful UHV chamber, ultra high vacuum chamber, that is equipped with UPS, XPS, electron energy loss. You can see here, this is where the holder, the sample holder is, the manipulator. You can extend it, you can rotate it. This is a UV source for UPS analysis, and this is the electron analyzer to analyze the emitted electrons. And so what we've been doing is we've been doing UPS analysis, so basically shooting UV photons on a sample, which could be either nanotubes or amorphous carbon, and then analyzing the emitted photoelectrons. And this has been done with helium lamps, and what we've been studying is the ratio of the fluxes of the emitted electrons between nanotubes and amorphous carbon. And we've been doing that as a function of the angle gamma, where gamma is the angle between the perpendicular to the sample, so that would be parallel to the direction of the tubes in the case of carbon nanotubes, and the direction of the incoming photons of the UV lamp, if you want to. And you can see here that this is the ratio of the two, so it's carbon nanotubes over amorphous carbon, and you can see that the ratio is 1. Different colors are just different electron energies, and you can see that as gamma approaches 90 degrees, this ratio goes up to 10 times. So it means that carbon nanotubes are emitting up to 10 times more when gamma is 90 degrees. So when the angle is grazing, when the photons are arriving at grazing angle on the top of the surface of the nanotubes. So this is further proof of the fact that carbon nanotubes have a strong anisotropy compared to amorphous carbon. Now, more detailed characterizations of nanotubes have been performed by us a couple of months ago in May 2021 at the Elettra Synchrotron in Trieste. We're still crunching the data, so I mean, this is still work in progress, and it's coming soon. Now, talking about the other side of the detector, yeah, the choice here is to find the optimal technology to measure KeV electrons in a compact way. Now, what we started to look at is to use avalanche photodiodes, APDs. Now, these have been designed initially as photon detectors, but with some small modifications can be also used for low energy electrons. For example, removing the protective window that would absorb electrons and stuff like that. You can see here, this is the Hamamatsu windowless APD that we're using, which is an active area there in the middle, which has a diameter of 3 millimeters. Now, APDs are simple and cost effective, so that's why we've been starting using these. But we're considering also alternatives. There's on the one hand SDDs, silicon drift detectors, which is similar technology, but they have a significantly better energy resolution than APDs. And they have been used for the detection of KeV electrons. You can see this paper over here. However, they're slightly more complex and they are more expensive to manufacture. And then we're also looking into microchannel plates. MCPs are an established technology for the measurement of KeV electrons, but they do have poor energy resolution. So here you can see we have been looking into this. We've been characterizing them at our facility, and but the results are still, you know, they've just been submitted. So yeah, they're not public yet. So to characterize the response of these detectors to electrons, we're still using this UHV chamber at LASIK Labs. We're not using the UPS, the UV lamp and the electron analyzer, but we're using this electron gun that you can see here in the image. This is a monochromatic electron source, which produces electron beams with energy between 30 eV and 1 keV, with an RMS on that energy of less than 50 milli electron volts. So it's really a monochromatic source. The gun current can be lowered as low as a few femtoamps. So this means that the electrons would be produced at a rate at about 10 kilohertz as the source is not punched. And the beam profile is small enough, it's sub-millimeters, less than 1 millimeter. So it's small enough that would be completely contained in the active area of the APD we're studying. And so here are some results. The first one I wanted to show you is this image here on the left. This is by keeping the APD off, so the bias is off, but we're still shooting this the electron beam all over its surface. And as a function of the place we're shooting, we're just reading the bias current of the APD, keeping it off. And so you can see that we not only see the central part of the detector, which is the sensitive area of the silicon, but we're sensitive to all the little details of all the electrical contacts that are around the wire bonding that you can see around the detector. So this is really proof of the fact that we have an extremely sensitive apparatus that we're able to see this even if the APD is off. And then once we switched it on, what we did was we measured and we shot the beam at the center of the silicon, and we measured the APD current as a function of the beam current. And you can see here a clear linear relationship, and so this is proof of the fact that the APD is measuring these electrons. These are 900 eV electrons. Finally, I wanted to leave you with a photo of a Dark-PMT prototype that we built in Rome. You can see here the picture. The idea here, this is technical design. You can see that the nanotubes would be are hosted here. Then the silicon sensor can be hosted here on a movable folder, and so you can also change the difference between the two. And there's a way of, and the tension can be set between these two things, just for producing this this cartoon that I showed you earlier. So yeah, this brings me to my conclusions. Carbon nanotubes offer exciting new possibilities for light dark matter searches. The key point here is that it's a two-dimensional material. It's made of graphene, and so if you get if you recoil, electrons would be ejected directly into the vacuum by a dark matter scattering event. I showed you this Dark-PMT detector concept. It has a lot of features. It's portable. It's insensitive to thermal noise, and it has directional sensitivity because of the direction of the nanotubes. In principle, we would be sensitive to electron recoils as low as a few electron volts, and this would make us capable of extending the reach to lower masses, and so particularly to masses lower than 40 MeV. So yeah, there's a lot of exciting R&D going on at Rome. As I showed you, there's a new CVD chamber with which we're producing a lot of nanotubes, and there's a new Dark-PMT prototype that has just started taking data. Thank you very much.